Yes, hello, good evening everybody. Finally underway. Right, I can see quite a few new faces tonight. Who's here for the first time this evening? 1, 2, 3, 4, 5, 6, you're not, but 5 of you. Excellent, welcome. So you have joined us at the beginning of the very first session of our second module. So we divide our course up into different modules, focusing on different aspects of C++. So we've just finished 6 weeks of what we call initial C++. That's when we're kind of starting from scratch. We are finished with namespaces in initial C++. I told you kind of enough that you needed to get on with namespaces. There is, as with everything we covered in that module, there is a lot more we could say about pretty much every topic, but the idea of it was to give a sort of a grounding in various aspects of the language that are necessary to go on and dive into more depth in specific modules, which we're doing, for example, today and for the next, yes. They'll probably be the same volume as they were in the last one, but if you want more, I can do more. Or I can certainly give more exercises for people to do on Thursdays. And yes, so if, I know Tom mentioned this, but for those who are new, we run 2 sessions a week at the University of Law. Firstly, today, we do this sort of lecture style thing. It's me standing at the front, in front of this very flashy touchscreen thing, giving you lots of information. And then we run another more informal session on Thursday evenings. It's just downstairs in the lobby area, which is like a more practical workshop session. So the idea is that you learn lots of new stuff today, and then on Thursdays you do some exercises, you practice what you have learnt in order to sort of, get it concreted into your brain, get a bit more understanding of how to use it, because again, people who've been coming for a few weeks have heard me say this several times, but learning programming it's a bit like learning a foreign language or learning a musical instrument, right? You don't get better at it in the classroom, you get better at it by practice. You get better at it with your hands on the keyboard trying it out. Yep, so if you're learning to play the piano, well, you can read all the books about music theory that you want, but if you don't actually sit there and spend the hours practicing, you're not going to get much better at it, right? So practice, practice, practice is what will make you good at any programming language, and C++ is no different. So yes, that's an aside. This is the start of Module 2. So welcome to everybody. If you are completely new to C++ and today is a bit like, whoa, I don't understand, well, it's because we've had 6 weeks of lessons already, 6 weeks of classes. So the good news is that all our classes are streamed live on the internet. We are broadcasting live now. Hello to anybody watching online. And videos for almost all of the 6 sessions are available on our YouTube channel, youtube.com/CPP London Uni. Unfortunately, we did have a bit of a technical issue with one of the weeks, but what's also available are all of my slides for the past 6 weeks there on our GitHub page, github.com/CPP London Uni. And then, I can't remember the name of the repository, but if you click on the repositories tab, it's the top one. It's called something like Course Materials Autumn 2019. So you'll find 6 weeks worth of PDFs in there with all the slides, with everything we covered. And also, if you come along on Thursdays, Ollie will be more than happy to help you if you have any problems with the material that we've covered so far. So just out of curiosity, those who did put their hands up for being new to C++, to being new to these classes, do you have some experience in C++ already, or are you kind of completely new to it?
I've done C++ like 15 years ago.
Okay, yeah. Well, it's changed a little bit, but you'll probably pick it up quite quickly. same boat, and a couple of you sort of shook your heads and said, never done any.
I touched on it many years ago.
Okay, do you have some sort of like programming background or no?
It's more a different branch of engineering support.
Okay, so for you today might be a bit like, whoa, I don't get it. But as I say, the past 6 weeks is all there. You know, please do catch up, and we're happy to help, particularly if you can come along on Thursdays. Again, for the new people, we have or we make use of a chat application called Slack. This is something we encourage everybody to join. So there's this, those who haven't heard of Slack, it's a very heavily used chat application. There's a CPP language, C++ language Slack chat space. That's got thousands and thousands of people from all around the world. And in particular, we make use of this. We have our own little room in there, which is #CPP London Uni. There's also another channel on there that's #learn, that's a really, really great resource for people who are learning the language. There are lots of experts in there who are really happy to answer questions, you know, even at 3 a.m. because there'll be someone in Australia who's awake who can answer a question for you. You know, so if you want to join that, and we do encourage everyone to do so, go to that URL that's on the screen, slack.cpp.al. It's got a little box on there. If you put your email address in, it'll email you a link so you can join that the Slack workspace. So really encourage everyone to do that. Right, so last week we were finishing off the initial C++ module. So we looked at, well, we had a bit of revision on const and references. So these type modifiers. We looked at this thing with an odd name, pass by reference to const, which is a really odd, long-winded way of doing what you want to do most of the time, which is to avoid copying when you're passing parameters to functions. You can pass a reference instead, but by passing a reference to const, a read-only reference, you can guarantee that that function is not going to modify the argument that you pass to it. Right? So passing by const reference, as it's usually known, is usually the way that you want to pass arguments to functions most of the time. We looked at the way that the const keyword and references interact with auto. So this is a way of deducing the type of variables. It's the auto keyword. The key thing to remember there, perhaps this will spoil what's going to come next, but the key thing to remember there is auto, plain auto will never deduce a const or reference type by itself. Right, so you have to put those modifiers in there yourself. And then finally, we very briefly looked at namespaces, what they are, what they're for, and how you can declare things in your own namespaces, and how you can call functions from other namespaces. So that was last week. This week, as I say, start of a new module, fresh start, very exciting. But there's one little bit of business from the last module we have to finish off, and that's our little fun end of module questionnaire. So we're going to spend the first probably half of this, maybe not quite half of this session on that, and then we're going to go on to the new material. Start on the new material, the new topic for this next few weeks, which is custom types in C++. And we're going to look at how we can define simple structs. We're going to talk about what structs are, first of all, how we define simple structs, creating variables of struct type, and how we can pass these things to functions and return them from functions. For those who were here last week, we did this little exercise in class, and we were a little short of time, so I promised you I'd give you the solutions next week. There were a few people who managed to do this in the allotted time. I don't know if anybody else took it home to do that. But what I basically wanted you to do, basically the point of this exercise was to sort of look at what the differences are between pass by value, pass by const reference, and pass by mutable reference. we can very quickly have a look at the solution to this. So here I've got three functions that all do the same thing. Print string 1, print string 2, print string 3. All of these functions print the string that you pass. The difference is in the way they take their parameters. So the first function here, print string 1, parameter type is a reference to a const string. This is this pass by reference to const thing I was just mentioning. Second function, print string 2, takes the parameter by value. And the third function, print string 3, takes a mutable reference, a reference to a mutable string. Okay, so we're going to try passing some strings to these functions and see how they behave differently. So first of all, we'll create a local variable called hello of type string, standard string. And then we're going to call print string 1. So we're just going to call this first guy up here, and we're going to pass this string hello. So first things first, is this going to work? It's not a trick question. This is going to work just fine. We've got a string, we're going to pass a reference to that string, and within the function print string 1, we can't modify the string, it's immutable, it's a read-only reference, but this works just fine. Yeah, we can't modify, in the body of this function, we can't modify the string we're given, but we don't need to modify it, we're just reading it, so that's okay. And we're going to call print string 1 again, and this time, instead of passing the name of a variable, I'm just going to pass this thing, it's called a string literal. And what's happening here is a bit more interesting, because in C++, a string literal, that is just some text in double quotes, is not the same type as a standard string. The reason for that is partly historical and also partly because a standard string can allocate memory behind the scenes, and that's not something we necessarily want to do. That's something in C++ we like to have very tight control of when things allocate or don't allocate. So this thing, just in double quotes, is a different type. It's not quite a string, it's convertible to a string. And in fact, what's going to happen in this case is that it's going to create a temporary string, and it's going to, from the literal, and it's going to print that string. So this is going to work okay, this second case. The double quotes is for a string literal, yeah. Well, if you didn't have the double quotes, yeah, it definitely wouldn't work, yeah. Okay, so now we're going to try the same thing again, our two variations with print string 2. And I've rather given the game away with the comment here, but this second version is going to work just fine as well. But this time we're passing by value. Remember, when we pass by value, the function receives a copy of the argument that we give it. So we've got our string hello world here, and when we call print string 2, we're going to pass a copy of that variable to the function. And again, this is going to work just fine, but it's probably doing a bit more work than we want to. As I just mentioned, standard string can allocate memory behind the scenes. That's not always something we want to do, something we want to control when it happens. So when we have a potentially large type like a string, we generally prefer to pass by reference rather than pass by value, because we can avoid copying. But it's okay, it works. It compiles, it does what we want it to do. And likewise, we can pass a string literal. That, again, will be converted to a temporary standard string, and that string will be used in the print function. So again, this works just fine. Finally, we can call print string 3, passing the name of this variable. And once again, in this case, this works okay. Within the body of this function, we are potentially at least allowed to modify the string. It turns out we actually don't need to. We're just printing it out. But in theory, we could modify the string, and that would result in this hello variable being changed, because references operate directly on the passed in variable. However, if we had declared this as const up here, if it was a const standard string, then this function call would fail. Because this needs a mutable string, and if we were to pass an immutable string, that would fail, because this function can potentially modify the variable. If we declared it const in the first place, then it can never be changed. So C++, the type system, would prevent us from making that call. Doing it the other way around, passing something that's mutable to a read-only reference, well, that's okay, because if we have something that's allowed to be, that is a read-write variable, and we treat it as read-only during a function call, that's okay. But the opposite, if we have a read-only variable and we try to treat it as read-write, that's not allowed. But in this case, this is read-write. This thing is a reference to something that's read-write, that's mutable. So this works okay. Finally, we get to something that doesn't work. And this is a bit peculiar, but was really the idea of the exercise to get you to notice this and to sort of perhaps scratch your heads and ask why it didn't work. So, we have a string literal. It's got a funny type. It's like an array of characters with a null terminator. But the point is, its type is not standard string. It needs to be converted to a standard string. And what happens in the previous two cases is that behind the scenes, C++ will happily go away and do that. And create a temporary string and just use it for the duration of the function call. And that works when we're passing by value, and it works when we're passing by const reference. It doesn't work in this third case. We can't, in the terminology, bind a mutable reference to a temporary. This has some quite interesting implications, and it's really the reason that C++ 11 ended up having move semantics, which we'll talk about a long way down the line. But the reason is really to protect you from yourself, protect you from making errors. Because if this is a potentially mutating function, let's say that instead of printing the string, it mutated, changed the string in some way, changed it to all capitals, for example. Well, that would work fine in this case. In the second case, it would do a very strange thing. It would have this temporary string. We change that in place, and then it would just be thrown away. And most of the time, that would be an error on the programmer's part. And so C++ actually prevents you from making that error by forbidding temporaries from working with mutable references. So this is a bit weird and takes a little bit of getting used to. And if you're sitting there and this is all like, whoa, what? I would advise you to have a bit of a play with this, sort of write your own example that's similar to this, and just try it out, perhaps with ints. Well, strings work just as well, and sort of work out which varieties of this C++ will accept and won't. it does make sense if you sort of think about it for long enough, but it's not necessarily obvious the first time you encounter it. So the idea of this exercise really was to make you aware of this behavior, and this is the reason I wanted to spend a few minutes going over it tonight, was that if you hadn't seen this, to really make you aware of it and to encourage you to just go and try it out and play with this yourself to work out when it's allowed and when it's not. That wasn't the only exercise, however, that I left people with last week. So Sard, you were, after more exercises and more homework, I left you with a doozy last week. You did it. Oh, excellent. Really? All of it? Oh, well done. Well done. Well,
How many people? Lift your hand. Don't be shy. Don't lie. You check.
Not all of it, but 2, 3 I managed to.
oh, excellent. Very well done.
What I was going to say was last time round there was more of those homeworks.
More of these really in-depth.
Because it makes you want to learn and think about
Okay, well, that's good feedback. So,
it. Go and research online.
well, so that's exactly the idea of me setting these quite challenging, like multi-part, very small text exercises. Is really that they'll usually start off with things that we have covered and go on to get you to look at things that we haven't covered, because with the best will in the world, we can't cover every aspect of C++ in 2 hours a week, right? So,
Was those exercises to actually really challenge or not put into practice.
okay, I will give you more hard homeworks. That's the feedback I'm hearing.
I didn't say hard homeworks, more
Sard wants more homework. Everyone's getting more homework. He's like the kid in the maths class who's like,
I just said more practice is beneficial.
okay. So anyway, the idea of this was to, first of all, give you some examples of passing by reference. So all of these, I wanted you to change a string in place, and have various various different ways that I wanted to change those by changing everything to uppercase or lowercase in the first case rather. Change things to headline case. So you had to iterate over strings and mutate strings in place, and I thought it was quite a fun exercise. Going over all of the solutions today would take an awfully long time because, as I say, it was a pretty in-depth exercise. The solutions, however, my solutions are available on GitHub. That should be one line. It's didn't quite fit on the slide, but github.com/CPP London Uni /initial week 5 homework solution. I know it was week 6, but we didn't get quite as anyway. That's the URL that has my solutions in it. So everyone who did the homework, very well done. You're more than welcome to go and check out how I did it. And if you come along on Thursdays, Ollie will also be able to talk you through exactly what I did and why I did it, probably, although he might look at it and go, what was Tristan thinking there? But anyway. But for those who did manage it, were there any, do you have any questions or any particular difficulties on that? Anything that made you go like,
I just spent a long time thinking what kind of
monster thinks up these things?
I thought more around, I got the logic and I wrote down like a pseudocode kind of thing.
Yeah.
A long time it took me, again, to think about it was what kind of control statements would work better, while loops or nested for loops or whatever. So that took a long time to get the
Okay, so if that didn't come out on the broadcast, you first of all thought about it in sort of kind of high level terms and then kind of translated it into C++ and had thought about like what kind of loops you wanted to use, while loops, for loops, do loops, whatever. Excellent, that is pretty much exactly what I wanted people to do. So that's excellent. And also the way I would recommend approaching problems, whenever you have something that's, like this, where it says, I want you to do this. Really good way of approaching it is don't start off thinking or necessarily start thinking in C++. Just think about it in abstract terms. What is the algorithm I need here? What are the instructions I need to do? Just work it out with a pen and paper first before you even touch the keyboard, right? And then once you've got that, you can translate it into C++. Right? Really good way of approaching these problems that initially you think, what? How do I do that? First of all, think it through, pen and paper, try it out, then translate into C++, is my advice. Okay. Excuse me for just 1 second. Ollie. Yes. It's showtime.
Is it like online or is it?
You've done these before, Saad. But,
Sorry, are we typing it in on ID or?
Oh yeah, so I'll go through the rules in a sec, so don't close just yet, I'll explain it first.
Yep.
Press now channel, save now.
Have we got a short URL?
Yeah, docu, I mean docu, whatever it is. That's a good URL short actually. Bit.ly.
Looking to sign in on this.
No, sure.
No, don't you?
Okay. Right, so the rules of this is if
Two seconds. Let me just put this on the slide.
you plug in the microphone.
Okay, so it's quiz time. It's the bit you've all been waiting for. End of module, definitely not a test. Fun time questionnaire, right? Not a test, not a test. All that happens is we ask you some questions about the material in the last module, and then we give you a score based on your answers, right? So definitely not a test. Everyone clear on that? Not an exam, not a test. Happy quiz, fun time. No, but seriously, this is a really good way for us to sort of understand kind of your level of knowledge. Like, am I going much too slowly because everyone's like, this is really easy? Am I going too fast because everyone's like, what the hell are you talking about? Right? This is the best way we have of getting feedback from everybody about how we're doing, and so we can tailor the next set of classes for your knowledge level. Right? So, as I say, not a test. Well, okay, kind of is a test, but really useful for us. So, yes, there we are. Anyway, over to Ollie.
Okay, so the basic principle here, as Tristan said, is it's to evaluate what you know. So don't guess questions you don't know the answer to. If you feel fairly confident in one, then obviously, yeah, go for that. But if you just have no idea, don't just randomly guess, because you might randomly get it right and think you're smarter than you are. And therefore make things harder on the next module, and that will just be bad for everyone. The other thing to bear in mind is that if you are presented with some code, some of the questions have some code for you to look at, don't copy that. However, if you have a question that requires you to write some code, do a bit of code, you are of course allowed to then go and write some code and paste that code in. However, that may be irrelevant for this particular test. I'm not sure I went that far this time. So that may not apply. But if you're given code, you're expected to look at the code and analyse it mentally. Don't just copy it and have the computer do the answer for you. That obviously defeats the purpose. Other than that, once you've submitted it, you will get a final score after I've reviewed it, because some of the questions I have to review manually, so they do require some input. But the idea is have fun, enjoy it. It will, hopefully reveal any gaps in your knowledge that you've got and confirm what you do know. Final question is really just for you to see if you've got a good idea of where
Okay, so this URL is on the screen, https bit.ly/34 lowercase c capital G V lowercase h. It's a Google form. Many of the questions are multiple choice. Some of them have some text you've got to enter, some code you've got to enter. We'll give you about 30 minutes, unless everybody finishes early. And it's going to ask you for your email address. That's completely private, but it allows us to email you your scores in a few days once we've had a chance to mark everybody's tests. If you can't get on the internet, put your hand up. Otherwise, off you go.
Should I not do it maybe? Because
Well,
just
if you are here for the first time, I mean, by all means have a look at it.
yeah.
But no, I mean, don't worry about it. And also if this is your first time here today, you are quite welcome to have a look at it. But if you feel that you have no idea what any of it's going on about, then don't worry too much. Yeah, if anybody needs extra paper.
I mean, you're welcome to do the test. I know it's you, so you won't skew the scores.
I suppose I should have a look at it, really.
Maybe as a word of advice, once you think you're done, just reread the questions to make sure you've read them properly. Yes. Sorry. So there are multiple kinds of language, right? So you might know statically typed as strictly typed.
Well,
No.
it's really asking the answer to the question.
So no, he doesn't understand what type means. So
Oh.
languages have types, right? Yeah. So in JavaScript and Java, right? So it says hey Java, right? We have string, we have int, those are types in Java, right? In C++ we also have those, right? So for example, in PHP, I can have 5 as a string, but then I can turn that into a number without doing anything. It just becomes a number. Dynamic thinking purposes. So I can tell you that, for example, PHP is a dynamically typed language. No, because C++ isn't PHP. Maybe C++ is actually.
Was that deliberate or a typo? Because that's fucking nasty.
No, it's deliberate.
Can you just tell them on YouTube as well if anyone's doing it that they need to finish now?
Those of you who are also on the stream, we will be closing responses very shortly. And anyone who has not yet done it, if you would like to do it later, you can contact me on YouTube. Contact me on Slack, not YouTube, and I can arrange it for you.
Okay. Let's call time. Everyone submitted?
Is everyone submitted?
Everyone who's going to? Yep.
Cool. Okay.
Do you want to go over the answers now or I'll leave it to next week?
Yeah, we can go with it now if you like. Do you want to go over the answers now, or
You have to be quite quick, that's all. But
who wants to go over the answers?
Hands up.
I'm interested in the if statement.
Okay, let's go. Bring them up. I'll go. I'll be quick. Oh, you can scroll as I talk about. Okay, so the first one, if he scrolls to it, got it. Which of the following is true about C++? Well, of course, C++ is statically typed, or strictly typed if you like. So that was the correct one for that. As in, you can't just magically turn a string into an int, for example. Which keyword is used for a function that doesn't return anything with no return value?
Void.
Exactly, it's void. So now, obviously, all of the statements that are not valid C++, right, the stuff that's bad. So int I equals 5, it's perfectly fine, right? So we don't check that. Const auto I equals 5, also completely fine. Const I equals 5, completely invalid, doesn't have a type. Auto const I, brackets 5.
this was mean.
This was a bit mean, but I want to see if you've done a little bit more research. This is in fact perfectly valid, so you don't check it. We then have auto I 5, that is again perfectly valid.
This is all actually even more mean because it's changed
Yes.
changed what it means, but it is
So
valid.
there is a bit of a clue though. If you scroll up, you can see it's worth 2 points. So the ones that were obviously wrong, right? So you should have seen this one, and this mutable thing you've never seen before. This one's also invalid. There's your 2 points. 2 check marks, 2 points. So declare a float, initialize to 4.2. Tristan, I'm sure you can take that away for us. Oh, not. Oh yeah, constant, yeah. Perfect, and a semicolon. Good measure. And then we can
This, by the way, is valid. You can say const float or float const. I'm just being fancy.
And then an alternative way, let's use auto for this one.
Why do you have to put F at the end of the float and not the other things like comma?
If you didn't, I'll allow it, but it would
Actually,
technically
that would be fine as well.
Technically, why do you
it would technically be an implicit conversion from double to float, but I'll allow it if you put it. It's fine.
This one would not be okay to leave it off. No, floats are in C. Auto, yeah, is new in it. So it's type deduction. If you're familiar with var in C sharp, it works a lot like that. Yeah. That was C++ 11, yeah.
2011. So we now have this piece of code. So obviously in main we've got a constant string that says hello. We then call add world, which takes a reference to a std string and it tries to add to it. So the question obviously is what's going to happen. So will it compile and run? Will it compile but have invalid behavior, undefined behavior rather, or will it completely fail? Obviously it's going to completely fail. You can't call this function because it's const, right? This does not want a const, and you have a const, so you can't do this. It's not going to compile. Yeah, compiler's going to say, sorry, you can't call this function.
This needs a reference to a mutable string. We've only got an immutable string, so we can't pass it to that function. This will fail to compile.
Precisely. So obviously for explaining your reasoning, you should have said what I just said, which is that you can't call that function with a const. string. Constring reference rather. Okay, so in stud : string, what is stud? And of course it is namespace. Yes. So let me ask which of those, are using automatic type deduction. Pick the correct ones. So again, as you can see, 2 points, only 2 of them are right. So we have, who thinks this one's right? Hopefully everyone. Yeah, that's the obvious one, right? We then have var, well this isn't Java or C#, so it's not going to work. Java 11. This is brace initialization. This is absolutely fine. This is nothing. Auto T is not a thing in the language. This is obviously valid C++, but it is not using type deduction. You have said that it's an int explicitly. So then for this particular if condition, you have to pick the ones that are going to satisfy it. So we first of all have auto x equals
3
true.
points, by the way. Did anyone notice that?
Yeah, 3 points, so 3 of them are correct. So we have auto x equals true if x, well, obviously that's true, right? If true, so it's good. We then have if
This
x
one's so
equals 5,
nasty.
if x equals 0, return true. Who thinks that's going to return true?
That you assign 0 to x.
Yes. So the trick was, and I gave you a little bit of a hint because you can see the difference between this one and this one. This is an assignment. It's setting x to 0, and 0 is considered false. So x gets assigned to 0. That's fine, but obviously 0 is considered false, so it will not satisfy the if condition. Then we have x equals false. If not x, return 3. Is that satisfied? Yeah, absolutely. X equals 5. If x is the same as true, if x is equal to true, return false.
Well, usually true is 1 or true is everything which is more than 0.
It's an int, right?
One is logical, the other is numeric.
Yeah, so the question is, can you compare an int and a bool literal? Well, ideally you wouldn't be able to, but in fact, and the compiler will probably warn you, but it is going to work. It's going to convert. X is not 0, so it's going to convert to true. So this is going to evaluate to true, and we get a tick.
Yeah, we got that one.
So sorry, it will convert 5 into bool. And 5 to bool 1. Is that what you're saying?
Yes, the true 5 is no, sorry, this won't. No, this
Well,
won't work.
it's
Sorry.
not.
Because true will be implicit.
Oh, you're all right. So it's the other way around.
Sorry, this is not.
See,
this is not valid.
I make mistakes with
You
this
threw me for a second there.
implicit conversions.
This one is not valid because it will convert
It's the other way
true
round.
to 1,
There you go.
and 5 doesn't equal 1, so it will not satisfy it. Remember, you have
Told you these were tricky.
So that was being a bit tricky. So now again we have this one, x equals 5, if x, well, in this particular case, it's turning an int into a bool rather than the other way around. Anything other than 0 is truthy. This is satisfied. And then finally we have the last one, just int x. So anyone want to tell me what's going on here if you want to give me a more nuanced answer?
It's x is
Uninitialized, yes. This is undefined behavior. So I said in the question, anything that is guaranteed to satisfy the if condition. And this is just pure luck.
It might work, it probably won't.
It might not. It might. Anything can happen. Sorry?
X is just initialized with junk. You have no idea, no possible idea what its value is.
Every time you call that function, a different thing could happen. If that was in a function, a different thing could happen every time. So now, considering this following code, let's try and speed this up a bit. We've got argument int a. We then create b from a. We then, in an inner scope, create c from b. So then the question was essentially which one lives the longest, right? So the first answer was a lives the longest, b lives not quite as long as a, and c obviously doesn't live quite as long as b. C, we can or is it the inverse? C lives the longest, b lives slightly less long, and then a is the last one to get destroyed. or they're all the same, or you're not allowed to use inner curly braces. Well,
A, the first one. A is
First
the
one.
longest.
the first one is indeed correct. So, and then
Do you know why?
that's an inner scope.
Do you know why the A leads the longest?
Sorry?
Yeah, because
It's a
C++
copy,
and
it's a
the
copy,
Y
but it gets destroyed before
needs
the
to
other.
destroy basically the most inner.
Compiler will release the memory for this one first, then it will release the memory for that one, then it will release the memory for that one when we return from the function. So they have distinct lifetimes. And then the question was, what is wrong with the above code? So who can spot any issue with that code? Exactly. The return type is int, but there is no return statement in there. And then we asked for a for loop that would execute exactly 10 times. I did notice somebody got this almost perfect. They accidentally inverted the less than. But I'll give you a point, wherever you are. So yes, there you go, and whatever inside it. The point was just to have a loop. And then the next one was you need to write a function which takes a constant ref and also a ref to a double, which then squares the int value. So just write a function, do return type double ref, and what do you want to call it? Okay, and then take an int ref, so int ref a double constant ref, sorry, constant ref a double ref b. Double ref b. Yeah. Okay, and then you need to do a times a. You can just make it a single one line if you want.
Hang on. Squares the int value.
Add 0.5 to the result of this. You could do it all in one line if you want to. So you can just do b equals that. I put brackets on it just to make it explicit for readability. So this happens first. Yeah. Return b.
Yeah.
Obviously, there's multiple ways of doing that. That's just one way of doing it.
It does tell you. Well,
You
yeah,
could do
actually.
return, you could just put return there and you're done. So you could one-liner. Anyway, there's multiple ways of doing that. This is why I have to read them. Okay, so.
But this is assigning to me. You just return.
No, you do return. No, so you put return in front of this entire statement. So just to demonstrate it.
Ah, okay.
Yeah.
But you don't have to use B. You could use just.
No, you have to.
No, it tells you to assign.
But would it make any difference?
Yes, because
you have to modify the variable
it tells you to
and return.
assign the.
Okay.
So that is one-liner, but there's multiple ways of doing it. As long as it achieves the same goal, that's it.
So
And then
has to take two numbers. It takes an int and a double.
So it takes an int and a double reference.
Yeah. Quick question.
Yeah.
In that case.
But it also returns a reference to the same thing as its function argument, which is a bit weird.
Yeah,
But
exactly. Because if you're modifying the B, which is outside, so what's the point of returning it anyway?
none, apart from maybe for chaining, as you'll learn later.
which would only be good for a member function. But yeah.
It would only be good on a class, really. But the point is to exercise your knowledge. Again, this is a test, not a way to write good. It's not. Yeah, don't actually do this with doubles in real life, right? These are to make you think, not to encourage you to actually do this in real life. And of course, hopefully, you guys have got through that. I'm going to start answering them while Tristan takes over and gives you the rest of the lesson. Cheers.
Yes. Which question? This one? Yep. If we were passing by value, that would be okay, but we're not. We're passing by reference. That's what this little ampersand here means.
If it was by value, it would take a copy
And
from
that-
the const, but it would then be useless because this would be a pointless piece of code, really.
Hmm. For an inner scope,
Mutexes.
yeah, so it's not something you do every day, it's not common. But what it does is it lets you declare an inner variable that gets destroyed at the end of that inner scope. And this is useful usually for the side effects of construction and destruction. So you want to have a variable that you know is going to be destroyed. So this is, if you know what RAII is, that we will spend time talking about, but basically it lets you acquire some resource in the constructor and free that resource again in the destructor and control precisely the lifetime of that. So again, Ollie says one of the things that is for locks and mutexes and things like that. But it could also be, you might also use, say, a unique pointer because you don't want to hold on to that memory for any longer than you need to. All right.
Are there any overheads with using inner scopes? Will it make your code?
No, I mean, if anything, it's going to be better because you're holding on to the variable for less time. You're using that memory for less time than you would if it had the scope of the whole function.
But runtime is the same.
Well, as I say, runtime would maybe be more efficient, and certainly not less.
Aren't we just using them all the time anyway? While loops and for loops and
Yes,
if statements.
you are. Precisely that. So for every time you use the curly braces with if statements or while loops or for loops, you are creating an inner scope. It's just rare. It's more rarely done just in plain code, but it is possible and legal to do, and very occasionally useful. All right. That was that. Let's go on to talk about some new stuff. Let's go on to talk about custom types, writing our own types in C++. And let's begin with a little bit of revision. So I'm going to spend quite a bit of time over the next few weeks talking about types. What do I mean by types? This is something that almost all programming languages have some notion of. And in its most basic sort of abstract definition, a type is a way of giving meaning to a piece of data. So computers only operate on ones and zeros. Your computer RAM, your computer hard drive is full of effectively billions of slots of ones and zeros. And we can look at, let's say, 32 of those ones and zeros and say, what does that mean? What does that represent? We can say, okay, these 4 bytes of memory, these represent an int. These 8 bytes of memory represent a double. These, however many bytes, represent a vector of strings. A type is a way of giving meaning to just numbers, effectively, ones and zeros. And I said this before in the earlier module, but you're probably already familiar with this idea, even if you've never encountered it in programming languages before. Because I'm sure all of you, when you're using your computers, you are familiar with the fact that files have different types, right? You might have a Word document or a PDF or an MP3 or a movie file, right? Well, on your hard drive, again, they're all just ones and zeros. But on Windows, the extension specifies the type of that file, what those ones and zeros represent, whether they represent a Word document or a movie or a PDF or whatever it is. And Windows, or your operating system, uses the type information to know what program to launch to try and read that. And it's exactly the same, or exactly the same principle applies when we're talking about types in C++. The type tells us what that piece of memory represents and what we can do with that piece of data. If we have 2 ints, 2 numbers, 2 doubles, whatever, we can multiply them, right? We know what multiplication means for 2 numbers. If we have 2 string variables, well, there's no, what does it mean to multiply 2 strings by one another? There's no, it's an operation we couldn't define. We don't have a good meaning for, right? So the type system will prevent us from prevent us from being able to call the multiplication operator on a string because it's not a well-defined operation. And C++ has lots of built-in types that are built into the language. These are what we call the fundamental types. And these are the ones that we've seen several examples of over the past few weeks. Ints, floats, doubles, bool. There are, in fact, a great many others that we haven't had any need to go into, but there are, you know, about 20 different integer types. It's crazy. Void is, in a funny way, a built-in type. These ones on the screen, by the way, are the ones that tend to be most useful and the ones that we have used so far in the course. Again, over the past few weeks, we've seen other types that are defined in the standard library. In particular, standard string, which just holds some text, and standard vector, which is a standard library type that's an array of some other value. It's a generic type that can hold instances of some other type. Right? You can have an array of ints, an array of floats, an array of strings, or a vector of floats, a vector of ints, vector of strings. And the C++ language provides us with many tools for defining our own data types, and that's really what this module is going to be all about. And in fact, the standard library uses precisely these tools to define types like string, like vector, like the dozen or so other container types that are available. So related to this idea of this notion of type is the notion of a data structure. And abstractly, we can think of a data structure as a way to organize the data that is used by your program. Right? And this is a sort of computer sciencey, quite mathematical, abstract notion of a data structure. And the data structures that we use, the way we lay out our data in memory, these can have really important effects on the performance of our programs and how easy or otherwise our programs are to write, or how easy it is for other people to use our code. You know, if you choose to use a linked list instead of an array, that can have performance implications. Some operations are very much slower on a linked list than on a vector. Other operations, well, one operation in particular, is much faster on linked lists than on a vector. So you've got to know your data, know the characteristics of the data you're going to use to be able to choose the right data structure to use. And selecting the right data structures and defining the relationships between them is an essential skill in writing good programs. And this is something that really only comes with experience, or becomes easier with experience anyway. Oh, that's fancy. There's a quote that I like from Linus Torvalds, who, you know, doesn't always say sensible things, but in this case I happen to agree with him. The difference between a bad programmer and a good one is whether he considers code or his data structures more important. Bad programmers worry about the code. Good programmers worry about data structures and their relationships. That is to say, or what I understand from this quote, is that the code can be much more easily changed. The data structures that you use, the fundamental sort of design of your program, That is much, much harder to change after the fact. So C++ and provides us with many tools which we can use to implement these data structures. Data structures typically are not something that you will come up with yourself, but they're things that have been researched by computer scientists, you know, often way back in the 50s and 60s when we're really first getting to grips with computers and what they could do. And there are libraries that will implement sort of any data structure under the sun. The standard library comes with quite a few different data structures, heaps and stacks and linked lists and hash maps and B trees and all sorts of crazy things. And there are libraries as well that provide these. And they all make use of these language facilities that C++ provides. Structs, classes, pointers, enumerations, arrays, unions. These are the tools that the language gives us to define our own types, to define our own data structures, to write well-performing, correct programs. And what we're going to focus on today and for the next few lessons is in particular structs and classes. These are the most fundamental in some ways and the most useful, the most flexible kind of custom data type that C++ provides. So you're probably already, you know, most of you, or anybody I would say who's done some programming in the past, has used any kind of language, is familiar with this idea of a struct, a class, a record, as they're called in some languages. So in C++, a struct or a class, it's a collection of data members along with what we call member functions that operate on those data members. Well, we're not going to be talking about member functions today. We'll get onto those in future. We're going to focus on the data members. We call those member variables. Some languages call them fields. These are the data items inside this structure, inside this struct. And we can define a new struct using the struct keyword, which is handy, easy to remember. And one thing that sometimes trips people up, or is perhaps unexpected in C++ compared to languages that came later, things like Java and C# and Swift and stuff, is that in C++ the keywords struct and class mean almost exactly the same thing, right? There are only a couple of little differences, and they're only to do with the defaults, and you can override those. So the keywords struct and class can be used interchangeably. A lot of people come in and they think, well, struct is like the C thing, and C++ is all about classes and object-oriented programming and that sort of stuff. That's not really the case. Struct and class are pretty much interchangeable. A couple of different defaults, that's it. So we're going to be using structs. Pretty much all my examples will be using the keyword struct. But I might slip and I might talk about classes. If you hear me talking about classes, I mean structs. If you hear me talking about structs, I mean classes, because they're the same, right? There is no difference in C++, other than a couple of defaults that you can tweak yourself. We'll see that probably next week, maybe the week after. So as I mentioned, we can define a new struct type using the struct keyword. This is introducing a new type into our program. We give our struct a name, and then we list its data members, its member variables. And the way we write these is similar to the way that we write local variables inside a function. So here I'm defining a new struct called point. Just represents like a 2D point, like on a screen or whatever. Point consists of two coordinates, in this case x and y, and these both have type int. So C++, it's a strongly typed language, statically typed language. When we define a new structure, it can have any number of member variables that we like, but we have to specify the type of those members. So in this case, they happen to both be ints. Oh, and one thing to note, because again, people come from Java and so on. Oh, why does it do that? In C++, a struct definition must always end with a semicolon. This is something that I forget like on a daily basis. You always need to put the semicolon in there. Yeah.
Can I have a question? This struct is something similar like Pascal record.
Yes. Yeah. Exactly that. Yeah. Yeah. So we're defining a new data structure, a new data type that holds, 0 or more data members. One thing to note in C++, again different from some other languages, that when we define a new struct, as we did on the previous slide, that introduces a new type that is distinct from any other type in our program. So even if we have two structs that have the same members, with the same types and the same names, those are still distinct structs, distinct types. So here we've got two struct definitions. They've both got a single member of type int, both named I. These two things have identical layouts, identical definitions, but they have different names. They are different types. A variable of type first can't be changed into a variable of type second, right? This is strong typing. So some other languages, types with the same contents can be used interchangeably, not in C++. If they've got a struct is a type, yes. Yes, yes it is. That's why I mention it. So I mentioned this, C++ places no restrictions on the number of member variables we have. We can have 0, we can have 100, 1,000 if you want. Probably not a good idea, might get a bit unwieldy. Think about different names for them all. But there's no restriction on the number or the type of member variables. You can use any C++ type. The two examples I've shown happen to use ints. But you can use floats, you can use doubles, you can use strings, you can use vector, right? We can have a struct whose members are of other struct types. And that inner one has members that are of other struct types, right? This is how we define these complex data structures. And in fact, that's why the built-in types are called fundamental types, because they're the ones that can't be kind of broken down into constituent pieces. They are the fundamental ones from which everything else is composed. So we can, in principle at least, use any C++ type we like as a member variable. I say in principle because there are things that are permitted but behave a bit strangely, don't necessarily do what you would want. So if we have member variables that are references, things get a little peculiar when we do assignment or try to do assignment. So it's best to avoid, not that you were thinking of doing this anyway probably at this stage, but it's best to avoid having member variables that are references. And if you want to, if you need to, as tends to be useful, if you want to have a member that refers to some other object elsewhere, pointers tend to be more useful for that. There's also this type called a reference wrapper that can be used if you are completely allergic to pointers. The other thing to mention is that you are allowed to mark a member variable as const. For example, we could have a const standard string as a member of our struct. This seems like a quite appealing thing to do, and in fact was a very common thing to do in C++ 98. Unfortunately, C++ 11 added these things called move semantics. We will be talking about those much later on in the course, but the trouble is const member variables interact quite badly with move semantics. Again, they work, but they don't necessarily do what you want. So, general advice, avoid member variables that are consts or references. That's the very short piece of advice, right? Stick to what you might call undecorated types for your member variables. Plain old int, string, vector, those sorts of things. So we can introduce a new record type, a new struct type, a new aggregation of variables using the struct keyword. Once we've defined our new type, we want to create variables of that type. Create variables, we also say we create objects of that type. Oops. Another way of saying it that's particularly common in C++, so we talk about an instance of a particular type. Right? These are sort of all different words for the same thing, effectively. But I will probably drop all these in when I'm standing up here talking, so I thought I'd put them all up there now so you know that I'm talking about the same thing in each case. Right? An item of data of a particular type. And we can initialize, we can create a new variable and initialize the data members, at least for simple struct types, just by using curly braces. So here I've gone back to this struct point that we had a couple of slides ago. Again, two coordinates, both ints. We've named them x and y. And now I've created a variable of type point. Now I've initialized the x coordinate to 1 and the y coordinate to 2. How does it know which one is which one? Okay, so we've said here that this is a point, right? So it's going to expect, well, it's going to expect two ints, and it's just going to read them in the order that they're written in the struct definition. So this one is x, that one is y.
So likewise, when we use in a program, so we will use b dot x, b dot y, or how is it?
Oh, that's the next slide. So in this case, we have this struct point, create just as we did before when we said int or string or whatever. We write the type, the name of the variable, and then it's got two data members, so we initialize those. In this case, x is going to be initialized to 1, y is going to be initialized to 2. Those who have seen some C++ before will know that I'm cheating a little bit and I'm dramatically simplifying the truth of the matter. Strictly speaking, this that has kind of half disappeared from the screen, I don't know why it does that. So annoying. This actually applies to what we call aggregate types. This is a subset of structs. Later on, we'll see that we can give structs private data, we can give them constructors, and in that case, the way we initialize them is slightly different. Initialization in C++ is unfortunately quite complicated. But for these quite simple structs where everything is public, we're not doing any inheritance, we're not messing about with constructors or destructors or anything like that, we have what they call plain old data. No tricks up my sleeve, just data members. We can use this half erased form of initialization of just saying, well, I want the first member to be that, I want the second member to be that, the third member to be that, etc. So this is the question at the front. Once we've defined a variable of type point, let's say, we can access those members using this dot operator. So here again, I've initialized, or p is a variable of type point, I've initialized x to 1, y to 2. And now we can access the x member of p by just saying p.x. So in this case, I'm setting the x coordinate to 5. So now our point P has x, its x member is equal to 5, its y member I haven't changed, so that's still equal to 2. This making sense so far? Yeah? Excellent. One of the goals of C++ when Struct was designing the language like literally 40 years ago, one of the goals was that you would be able to use your own user-defined types anywhere that you could use fundamental types, built-in types. That there should be parity between user-defined types and built-in types. Built-in types shouldn't be special. So we can use struct types anywhere that we can use fundamental types. For example, as a member variable of another struct, as I just mentioned. This is how we can build up complex data structures. Yeah.
Like here, lowercase p is an instance of type
Point. Yes, absolutely. Sorry? Type point. Yes. Yeah, absolutely. So we can use our struct type as a member variable of another struct, or as a function parameter, passed by reference or passed by value. We can use our struct type, for example, as the element type of a standard vector. We can have a vector of ints, a vector of doubles, we can have a vector of points. So let's have a slightly lengthier example rather than just a couple of lines. We'll expand a little bit. So here I have defined a struct called example. And example has two members. A member called str of type standard string, and a member called value of type int. And I've given these default values. We'll see in just a second when these come into, how these come into play. So first of all, I'm creating an instance of type example. So this is a variable named ex1, so of type example. And I've set ex1.str to the string a and the value member to 1. So this is exactly what we just saw on the previous slide, except with a different type this time. We can also write it like this, because as I said, initialization in C++ is weird. In C++11, we're allowed to leave out the equal sign and just write it like that. And this is very common. You'll see this all over the place because people don't like to type more than they have to. So we're actually allowed to omit the equal sign and just say ex2 curly brackets and then the initializers. So you may find me writing things like this from now on because that's the way I most commonly do it. We can actually supply fewer initializers than we have members. So here I'm saying ex3 is of type example, but I'm not supplying any initializers. So in this case, both of my members are going to get whatever their default values are. So in this case, str is going to have the value default, the string default, and the int member is going to be initialized to -1. And actually, another thing we could do, I don't have a line for it, but we could say, for example, ex4 curly braces hello, and that would initialize the string member, but leave the value member to be defaulted.
Can I say X4 curly braces 2?
No, not in C++ yet. C++20 you will be allowed to do it. And in fact, C allows you to do it, and most C++ compilers will allow you to do it as an extension, but it's technically not part of the language until 20. But as an extension, and what will be in 20, is that you'll be able to say ex3 curly braces dot value equals 17 or something. But that's a thing for the future, and I will update these slides in a couple of years' time when we've all got C++20 compilers. Do you have a question, Si? Okay, well, don't worry about that. That's a future thing.
The main thing you explained is if you leave it empty, it will go default to the original value.
You get the default, whatever the default values are in there. Just as with fundamental types, we can declare variables as const. So we can have a const example. So this is an instance of our example struct that cannot be modified after we have initialized it. So if we say ex4.str equals hello, if we try to change one of the members of our struct, we're going to get an error. The compiler is going to refuse to compile our program. It's going to give you an error message. It's going to say, you're trying to change this, but ex4 was declared const. You can't do this. Right? This is part of this const correctness thing I was talking about last week or the week before. But ex3, this guy up here, well, this one isn't const, so it's fine to change that, to mutate it. So we can change its str member to hello in this case. The other thing we can do is to create references. So in this case, this variable xref has type reference to example. So we talked about references a couple of weeks ago and again last week. A good way of thinking about references, if you haven't sort of come across them before, is that a reference is in many ways like giving a new name to a piece of, to an existing variable. Right? Anything we do to a reference modifies the original variable. Yeah. Oh, sorry, it should have been ex1. That's a typo. It's meant to be that one. Sorry, I will change that. Thank you. Yes, that's better. Thank you for that. So we're declaring this thing to be a reference to our variable up here. So now ex1 and exref are two names for the same piece of data in memory. And we can use that reference to access the members of the struct. So exref.value, we're going to set it equal to 22. So we're accessing the members, the member of ex1, but we're doing it through the reference. So these screens are sort of lovely, but just a bit small if you're sitting at the back. It's slightly. Oh, it's got things plugged into it. I don't really want to move it. But for those who can see the bottom line, does anybody see the bottom line? Okay, so the bottom line says, well, we're effectively we're printing ex1.value. And the question is, what does this print? Well, it's going to print 22 because ex1 and exref refer to the same bit of memory. So when I change exref.value, that's changing ex1. They're two names for the same piece of data. Anyway, that's a little bit of a revision about references. The point I wanted to show on that last little example is that we can form references to our own data types, just as we can form an int ref or a float ref. We can have, in this case, an example ref. So we can declare variables of our own custom type. We can make them const, we can form references to them, just as we can with the built-in types. The other thing that we can usefully do, or really quite essential, is we can pass structs to functions. And we can return structs from functions. Again, we want to be able to use our own custom types just like we can with the built-in ones. So, just a reminder, of course, C++ passes by value by default. And this means that if we pass by value, that structure and all of its contents will be copied into the function. Right, that's what pass by value means. And as always, in fact, as we saw in the little quiz earlier, if we want to pass by reference, we need to specify that the function parameter is a reference, has this sort of ampersand as part of the type name. And of course, we can form const references just as we can with fundamental types. This entire slide is saying your own structs are just as good as the built-in types, and you can use them in exactly the same way. And if you're happy passing ints by value and by reference or floats or whatever, then that's how your custom types, your structs that you define, work as well. Come on. So, apologies that this is very tiny for those at the back. Got another struct example. This one's very slightly different to the other one. This time we've only got a single member of value. I got rid of the string because it was taking up too much space on the slide. Unfortunately, things were a bit small anyway. But now I've got a function that makes use of our custom type. So I've written this function called setVal. Takes two parameters. First parameter is of type example, and the second one's an int. And inside this function, I'm setting the value field of ex to be equal to the passed in value. And now I've got another function called setVal2 that does almost exactly the same thing. Except this time I'm passing the first parameter by reference instead of by value. The first parameter type is a reference to example, not just an example. So now we're going to create a variable of type example. And just to be fancy, this time I've used the auto keyword, really just to show you how it works. There are some people who really strongly advocate using auto almost everywhere, almost always auto style, they call it. And this is something that C++ programmers have like endless fights about, like tabs versus spaces. Some people really like the auto keyword, some people hate it. Some people advocate using it almost always. And when they do that, they suggest that you should write your variable declarations like this. So you say auto name equals, and then you say what type you want on the right-hand side. Well, take it up with the AAA people.
I would like as the first example. The example is the void set var, the first one. Yeah.
Yep.
Example is the type of x.
Yep.
And further on, we have to give all fields of example or x what we will change or initialize. Right? Am I right?
We're being passed an instance.
Arguments, or how do we call it?
In this thing here,
So over there, we need to give all fields of example.
I'm not sure what you mean by all fields.
Elements of example.
Well, we're being handed an instance of example that we assume all its fields, in this case just the one, have been initialized.
Yes, but we have only just one int value, but we can have more.
Yes, we could have lots and lots of members.
We have to mention all of it on the list.
Well, we can omit some, in which case they will just get their default value. In this case, yes, we've specified all of them, which is only one. Yep, so as I was saying, this is an alternative way of defining a variable of type example with the field initialized to 3. Really just to show you that it works and that some people advocate using this style. Whether you like it or not, I guess is a matter of taste.
Do they advocate to use it with classes and struct, or also with like fundamental types?
Almost always. With fundamental types, with everything, yeah. Okay, so we got our variable ex, so type example, and we're going to call setVal ex, and we're going to pass the int 99. And then we're going to print out the value field of our variable ex. So the big question is, what is this going to print out? Sorry?
I think is missing over there, setVal x, the type is missing.
The type?
Yeah.
Well, this is a call to the function, so the compiler knows the type of the function, the type of the arguments it's expecting, because we've declared the function up there. So we're just calling the function. Is it going to? All right. Is it going to print 99? Oh, you basically got 3 choices, right? It could be 0, it could be 3, it could be 99. Those are the numbers that are on the screen, so those really are the only choices you've got. Let's rule out 0, because that's just the default value, and we're not using it because we're explicitly saying, right, so is it 3 or is it 99? Well, the answer is this prints out 3. Who can tell me why it prints out 3? We're not using, absolutely, we're not using a reference. So this is passed by value, so it's going to get a copy of our example instance. It's going to get a copy. We're going to modify that copy, which is pointless because we're just throwing it away. After the function returns, this copy is destroyed, discarded, so nobody's ever going to see the changes we made to it. Oh, and I've given the game away, but you were all smart people and would have guessed what I was going to do anyway. Is that if we call setVal2 instead of setVal, call this second function here, well, this time we're passing by reference. So now we can modify the fields, modify the member data of our struct, and because we're passing by reference, those changes are now visible after the function returns. So again, just as we had those examples of passing ints by reference, passing floats by reference last week, we can do exactly the same with our custom types. Again, pretty much all the things that I've shown you over the past 20 minutes or so have just been to emphasize and reiterate this fact that in C++, as far as is possible, custom types behave in the same way, or unless you opt out of the behavior, custom types behave the same as built-in types. And I stress that because it's not the case in many other languages, but it is in C++. Okay. I have 15 seconds to finish today's material. Sorry? Well, 5, 4. All right, here we go. This is actually a good place to finish because I had an exercise that I was going to give you, but now it's going to be your homework. So yay! I know it's not hard enough for you, Saad. I'm really sorry. I will. This was supposed to be a class exercise, which I generally make a bit easier because time limitations and stuff. I'll come up with something really, really nasty for you next week. Don't worry. Something you can really dig your teeth into. So if you're all struggling with next week's homework, you know to thank. Anyway, if you by all means take a photo of this, I'll leave it up. Leave it up on the screen for a few minutes. Sorry. Yes, I'll pop the slides up as well on the GitHub page, and I will post the link to that in the Slack channel because hopefully everybody joined that. So that is it for today. Thank you everyone for coming. It's been a slightly different session to normal with the little test, the little questionnaire that I'm sure Ollie has been busy marking for you.
Yes, everyone has their marks.
Oh, everyone has their marks already? Oh, excellent. Yeah. So obviously I've been told, I don't know how well you've done, but I'm pretty confident many of you will have done very well. So for those of you who are here for the first time, I hope this hasn't been too overwhelming. As I say, you're more than welcome to look through the material from the past few weeks. Come along on Thursdays. Ollie will be there to help you out with any questions you may have. Other than that, that's it for this week. We're, as usual, going to visit a local establishment for refreshment afterwards. Each and every one of you is welcome to join us. Other than that, that's it from me. Thank you very much. Cheers.